Hi, this is Shelley Physics, episode on conservation of energy. We're going to look at how the work kinetic energy theorem works in several different systems and produce this expression called the law of conservation of energy that's very useful in many different applications. One of my favorite applications of law of conservation of energy is roller coasters, and this is one of my favorites from Busch Gardens in Williamsburg, Virginia. It's called the Griffin. Now, all roller coasters start out with doing some kind of work to the system of the riders in the roller coaster. Usually it's like this with a chain and a motor. Sometimes there are these linear induction launchers that just send the coaster flying. In this case, we're just lifting up the riders to the very top. There's work being done against the weight of the riders, and that's the work done by the chain and the motor. That puts energy into the system. But you'll notice at the very top, they're not moving very fast. This work isn't done to change the kinetic energy of the riders, but it does change the potential energy of the riders. So they have the greatest amount of potential energy at the top of that ride because of the work done by the chain and the motor against their weight. Now, the unique part about this ride is that the riders are held at rest just before plummeting at a 90-degree angle down that first slope. And that's why the first drop is always the best, because it has to be the highest due to those non-conservative forces throughout the ride. When it goes, that potential energy converts directly to kinetic energy, and you got the fastest point on the ride. This one swishes and swirls, goes through water, takes another 90-degree dip. I love this ride. So let's look at it in terms of work, the work done. Now I threw out three key terms in that introduction there: work, kinetic energy, and potential energy. You don't necessarily need to know these coming into this presentation, but I'm going to show you the origins of those three words. And they come from Newton's second law of motion, which we've just talked about, and equations of motion. You just put those together and we get this tool, this thing we can use to further our understanding of more complicated scenarios, like, roller coasters that go up and down and all around, banks and turns and all this kind of stuff. So when you're designing a roller coaster, how do you know how fast it's going to go? You got to be able to plan for that. That might be the focus of your entire roller coaster. This is going to be the fastest coaster ever, the highest, fastest thing. And that's what roller coaster designers will often do. So first off, I talked about this quantity called work, and it's really coming from Newton's second law. I'm going to try to go through this as quickly as I can here. So sum of all the forces acting on a body equals mass times acceleration. I'm just going to simplify that to net force, F net. It means the same thing. Sum of all the means the net. All right, so with net force, you might recall that for acceleration, there's one way to look at acceleration. It's in terms of final velocity and initial velocity. But when we're looking at a displacement, that's the important thing with a roller coaster, is that when you compare like the top to the bottom, there's a difference in position. There's a displacement that happens as it falls. So we're going to look at what I often call with my class the third equation of motion from our motion unit. Final velocity squared equals initial velocity squared plus 2a times displacement. It's a delta x, change in position. Now that's like an x final minus an x initial. For this discussion right now, I'm just going to use an x, okay? X for displacement. So that might be sort of familiar for you. Now if we rearrange this to solve for the acceleration, I'm going to subtract initial velocity from both sides to get final velocity squared minus initial velocity squared, just doing some algebra here, equals 2ax. And now if I divide both sides by 2x, I'll cancel out that 2x on the right, and we'll get left with it on the left. So the 2 cancels, the x cancels, and I get acceleration equals final velocity squared minus initial squared divided by 2x. Okay, so what we're going to do is take this expression and substitute it into Newton's second law. Measuring acceleration of a roller coaster is probably kind of hard, but measuring speeds, well, at the top, that coaster was 0. At the bottom, we want to know what the speed is going to be at the bottom, at the fastest point. So I got net force, we're going to plug it in, equals mass times this little monster over here, final velocity squared minus initial velocity squared over 2x. All right, now I'm going to just bring this x character up to the other side and distribute the mass a little bit. So first, like I said, I'm going to multiply both sides by x. We get net force times displacement, okay, times an x equals. All right, I've got this 2 in the bottom and I got a mass up top. So if I distribute this m to the VF and distribute it to the VO squared, then what we're going to get, I'll go ahead and do that first, algebraically speaking. Divided by 2x. Oh, oop. What I should have done is canceled out that x. There we go. Divided by 2. All right. Now a couple things. First, one thing I'm going to do here is separate these two terms. Okay, I'm going to pull them out. And when talking about a roller coaster, if we're going to go up a hill, we're not really displacing in the x direction where all the forces involved. You see, the chain is there to pull the coaster up. There's usually some kind of chain here and it's working to pull the coaster up the track. So the force we're going to be working against is that vertical weight force. That's what the roller coaster works against. So instead of an x, I'm going to call that a y. Let's call this the y direction. That's going to be the direction of change. This 2ax is usually talking about like horizontal motion, cars speeding up, slowing down in the horizontal direction. All I'm going to do is just change that letter to call it y, because that's where all the motion is going to happen, in the y direction. So we have a net force times y. Just make one little change there. Equals. And this 2 under the bottom is like a half. It's 1/2. So if I pull out that 1/2 and attach it to the mvf squared. And you might also know that this term is being divided by a half also, since I'm factoring out that 1/2. Factor out a 1/2 on this term and I get an mvo squared times a half. What we have now is an expression that's set up. It includes mass, initial and final velocities, force applied, and the displacement. Now all those things are involved with a roller coaster. As it goes up a track, as it goes down a track, well, later on in the track, when it goes up a little hill, once it's moving, it slows down. There's a change in speed. When it goes down a hill, it speeds up. There's a positive change in speed. So there's going to be changes in speed. There's a mass of the coaster. Remember, the mass is kind of important here because the mass is what's being lifted up the hill. And also it's being accelerated. That's the mass here is where that m came from in the first place. And we got to consider this force to lift the coaster up the hill. There's a chain, there's a motor. Also, to bring it down the hill, to make it go fast. That's the fun part of a roller coaster. It's not really, oh boy, I love going up the hill. That's not usually the best part there. But going down the hill is definitely gravity, and there's also displacement. So all these things are involved in this motion. But what comes out here is a quantity 1/2 mv squared that relates force and displacement to something about the motion of that mass, motion of that roller coaster in this case. And that's what we're going to call the kinetic energy. See, kinetic energy is dependent on velocity. Velocity alone, mass and velocity alone. All right, so that is one thing we're going to hold on to. And now, let's talk about this character over here. What force is involved in lifting up a coaster? Well, the heavier the coaster, the more force you need, right? So this is the weight force in this case. Weight. And weight is mass times acceleration due to gravity. And in this particular situation, the y we can probably more commonly call the height of the coaster. Okay, so we're going to, again, transform. There's a little transformation going on in a couple of steps here. Transform that y into a height. So the height later on, after it gets to the top, equals a change in kinetic energy. Now, where this is more useful to talk about is the fun part of the ride, when it goes from the top to the bottom. You see, going up is the opposite of going down in a sense. Okay, so if we're now going to go down the other side of the track, okay, you usually don't go up, you go down the same way you go up. There are a couple rides like that. Actually, there's one at Busch Gardens called Tempesto. And that one launches you off, kind of shoots you off, and you go up, and you go right back down, and launches you again, going backwards. You go up higher, and you go back down. Kind of takes you back and forth until it gives you enough speed to go up over the top of the rides. I think it's a whole lot of fun. That's a great ride also. Okay, so anyhow, we have this mgh equals 1/2 mvf squared minus 1/2 mvo squared. And you might notice that, well, you know what, let's put this in a new context here. Let's put it in the context of a roller coaster going down from the top of the hill to the bottom of the hill. Here's our top, and here's our bottom. Now in this particular ride in Griffin, at the very, very top, the initial velocity up here is 0. So that's just one initial case. A lot of roller coasters, though, you might have seen that the roller coaster, after it went up the hill, it kind of went around that kind of, here's the up part, went around the corner before it fell down. So oftentimes coasters are moving along with some kind of initial velocity. Okay, so initial velocity might be something like, 2 meters per second or something like that. It's usually going real slow, or in this case it was stopped. But at the bottom, this is where there's a lot of speed down here. And that's often what we want to know. Is there a way to tell the final velocity by the height of the track? You might notice if you ever jumped off of some kind of platform, let's say it's 2 feet high or 4 feet high, you notice that you hit the ground harder from the greater height because gravity is accelerating you faster and faster and faster. That expression on the previous page, here's what we had. mgh equals 1/2 mvf squared minus 1/2 mvo squared. Now look at this. This is an initial condition. All right, it's the initial velocity at the top. Well, there's often a height involved with a roller coaster as well. If this roller coaster is like 100 meters tall, there's an initial height. So this height over here, talking about gravity doing some work on this side, that gravity is going to accelerate it. So the mgh here is going to be gravity pulling down, changing the velocity from 0 or something really low down to some final velocity later on. We'll call this the bottom of the track here. Okay, at the bottom, let's say the final height is 0. So we're going from like 100 meters down to 0, and the velocity is going from maybe 0 up to what? How fast would a coaster be going if it rolled down from 100 meters high? So what I want you to reframe this to look like is I'm going to put all the initial conditions on one side and all the final conditions on the other. And let's see how that changes things around a bit, because this is also an initial height right there. So I'm going to put these two initial conditions together on the same side in the beginning on the left by adding 1/2 mvo squared to both sides. That's an addition sign right there. We're going to add it to both sides. And what we get is mg, initial height, plus 1/2 mv squared, that's the initial velocity squared, equals 1/2 mvf squared. All right, so far I haven't really done any math here, but what we've got here is all the initial conditions on one side and the final conditions on the other. I've already talked about this as being called the kinetic energy. And because it's a final velocity, this is the final kinetic energy of the system. This would be the 1/2 mvo squared, would be the initial kinetic energy of that system. So what is this character over here? Well, do you think we can add velocity to energy or height to energy? It turns out this mgh is also an energy. I can prove it to you with units. Do a little provation over here. I just made that word up. The units of mass is kilograms. The units of acceleration due to gravity is meters per second squared. The unit for height is meters. So if you multiply all those together, we get kilograms meters squared per second squared. Now what about this creature over here? 1/2 doesn't have a unit to it, but mass does. The unit for mass is kilograms, and the unit for velocity is meters per second. And look at that, we square both of those. So it turns into kilograms meters squared per second squared. We got to square the numerator and the denominator there. So you get out the same exact unit. That means this is some kind of energy as well. What kind of energy could that be? It's not energy due to velocity. It's an energy due to position. And that position comes from gravity. You see, this is a gravitational force applied to a displacement, which is something called work that's done. That chain has to do work to lift the coaster up to the top. Some kind of like gear and pulley, chain system here. So these are energies. And once you get that coaster to the top, nothing else has to work on the coaster except for gravity. Whenever you lift something up and leave it alone, it does something. It just fell on its own. Well, it's actually gravity pulling on it. If I put it on, my hand and leave it alone right there, it just stays. Okay, so from my hand, there's nothing happening. But if I lift it up and leave it alone, it falls. So if I lift something up, what I'm doing is I'm doing work to it. I'm doing a positive work to it to lift it up. But as I lift it up, it's not moving at the top. Notice there's no change in velocity when I lift something up. It seems like there's no change of velocity because actually, as I lift it, the net force remains 0. Another way to look at this, though, is that as I'm lifting it up, I'm increasing its potential energy. But as I let it go, that potential energy decreased again. And what I mean by potential energy, see, this potential energy is due to gravity. And the reason it's not getting faster is because as I lift the pen up and do work to it, gravity is doing negative work to it. It's always working against you. If you go and take a step up the stairs, you put energy to lift yourself up. You put energy into it. Now, usually when you take a step, it launches you forward. Your velocity changes and you keep going. That's why when you're running really fast, you have to take a moment to slow down or else you'll trip and fall and hurt yourself. Your body keeps on moving because it's got a lot of kinetic energy. That's one way to look at inertia. It's a body with a lot of kinetic energy tends to remain moving with a lot of kinetic energy. But gravity is working against you when you're stepping up. So you tend to slow down as you go higher, as you try to step upwards on a step. And that's what's happening here. Yes, this chain is doing some positive work. There's positive work from the chain. And that's the mgh. That's the amount of positive work. But as the coaster goes up, there's some negative work from gravity. That keeps it nice and slow. But you see, this force that's slowing it down, gravity, it's not like friction. When you're sliding along, friction will slow you down and you'll stop. But you won't come back to where you started. Friction's not going to launch you backwards. But gravity slows you down and then speeds you back up. See, if friction were like gravity, you could take a box and you could push it against the floor, and it would slow down. And like I said, if it were like gravity, it wouldn't stop there. It would speed up and then come back and smack you. That's what gravity does. If I toss something upward, it doesn't stay at the top. It comes back down immediately. That means there's a potential energy that's built up due to that special force. Gravity is called a conservative force. It's not really important now. But the main thing is, we got one more piece to our puzzle. Potential energy from gravity, we can call mgh. Kinetic energy, again, is 1/2 mv squared. Now we're getting somewhere. And one more thing. All our initial conditions, remember this is initial gravitational potential because it's a initial height. These are all our initial conditions of energy, and this is our final condition of energy. So what do we see here? That if we just take the initial energy of the system that'll equal the final energy of the system. And usually when I do physics, things get more and more complex, but now what am I doing? We got sort of a complex equation here, but I'm describing this first term as potential energy, and these two terms, they look similar. They're kinetic energies in the initial and final state. Now we're looking at, put these two initial conditions together, we get the initial energy of the system, and we get the final energy of the system. And it turns out, if you've got a whole roller coaster, and it comes back to the end, if we look at any point on that coaster, 0, 0.1, maybe at the bottom down here 2, at the top of this loop 3, and look over here later on 4, and maybe at the end 5. Guess what? The energy at any one of these points is equal to the energy at any other point. So the energy at the first point is equal to the energy at that second point. I'll call them first and second, but this is the 0th point and the first point. And then we get the second point is equal to those, is equal to the energy at the third point. Now I can go on here, but I think you see the pattern is equal to the fourth and the fifth. Now those forms of energy might change. Potential energy is dependent on height. And you see there's different height changes here. So potential energy is greatest at the top and least at the bottom. Definitely at the bottom here at 0 and 5. Those are the very bottom points. Kinetic energy though, where is it the greatest? Kinetic energy is the greatest at the bottom and the least at the top, because the velocity is the greatest at the bottom of the hill and the least at the top of the hill. So for the system, we have the energy at one point equals the energy at any other point along the track. And this is called the law of conservation of energy. It's telling us that while the amounts of potential and kinetic energy might change, the total energy in the system always remains the same. So we're going to do an example, an application here with the roller coaster. Let's go back to that example I gave just a moment ago. Well, the way Shirley talks, it's a little bit more than a moment. Let's take an initial velocity of 0 at the top of a 100-meter high hill. What will the velocity be at the bottom? And I'm going to call the bottom down here, this is a height of 0. So let's go backwards now. Let's compare the energy at the beginning to the energy at point 1. We'll call this point 1 down here and point 0 up here. Okay. So we say to ourselves, this is what you do. What kind of energy is at the top of the hill? Is there potential energy? Is there kinetic energy? And here's how you think of it. The potential energy is mgh. Kinetic energy is half mv squared. Write those down first. And you think to yourself, is there height? Does the object have a non-zero height? at this point? Yeah, it does. So there's going to be some gravitational potential energy. There are some other kinds of potential energy. We're just talking about gravitational in this activity. But I'm still going to put a G on there. So you keep that in mind. There's a G for gravity. Is there any kinetic energy? Well, does it have velocity? At the top? No, it doesn't. So all the energy is just potential at the top. Getting a lot of stuff drawn in here, so I'm going to just circle that with a different color so it pops. How about the bottom? At the bottom, the height is 0. So is there any potential? Nope, no potential down there. But is it moving? Does it have velocity at the bottom? From experience, when you roll a ball down a hill or a roller coaster down a hill, yeah, it's going to have velocity. So if it has velocity, it has kinetic energy. See, there's mass in both cases. Mass of an object can't be 0, or else the object's not an object. You can't pick it up or whatever. So potential energy depends on height. Kinetic energy depends on velocity. There's going to be just kinetic energy at the bottom. Circle it. All right, now we can go over to this energy equation over here. Yeah, that's what it is. Energy at one point equals energy at the other. And in the beginning, there's only gravitational potential energy. I'm going to put a 0 here to say it's at the beginning. Just keep that in mind. Keep that in focus. And at the end, at point 1, there's only kinetic energy. And that's at point 1. That's it. And that's how you set it up. Substitute in your potentials and kinetics for each of those. Now, all right. Now, substitute in mgh for that potential energy, gravitational potential energy. And because it's in the beginning, this is going to be a h0, an initial height. And that's sure enough what it is. It's the initial height of the roller coaster. And kinetic energy, we're going to substitute in a half mv squared. And this is at point 1. So I'll put a little 1 there. That's important because later, if we introduce a velocity in the beginning, there's going to be a v0, a v0 at the beginning, and a v1 later on. So we want to differentiate between those two. Just practice doing that. And now, guess what? We can plug in what we know. Mr. Shelley, what about mass? You know, when you think you're stuck, don't stop there. Don't get caught up on that, because it turns out whenever there's this thing in physics that whenever a problem doesn't give you mass and you think you need it, oftentimes you're going to find that it cancels out and you actually don't need it at all. And that's what we're going to have here. There's a mass in each of these terms. And whether that mass is 1 or 2 or 100,000, okay, it's going to cancel out. So let's just leave it in there for a moment. At G, we know what G is. Acceleration due to gravity is 9.8 meters per second squared. So I'm going to substitute in a 9.8. All right, and we got the height. The initial height is 100. Then we have this mass over here that we don't know what that is. And we got this velocity, we don't know what that is. But guess what? That's what we're looking for. What is the final velocity? In other words, what's the velocity at point 1? That's what we're looking for. All right, at this point, we could go ahead and divide both sides by m. And I'll cancel that out. So make that nice and visible there. And 9.8 times 100 is not 9,800, it's 980. Move that decimal point over twice, we get 980 equals 1/2 velocity at 1 squared. And look at this. We could solve that. That's some algebra right there. Multiply both sides by 2. I'm going to go ahead and do my algebra in purple because I already started that. And multiply both sides by 2. 2 over 1 times 1/2. 1/2 of 2 is 1, so those will cancel. And I got 1,980 times 2 is, 980 times 2 is 1,960. And that's not the velocity. That'd be a very quick velocity. That'd be almost 2 kilometers per second. But this is, 1,960 is equal to velocity squared. So we're going to take a square root of both sides. It's my algebraic operations. and we got a V1 equal to the square root of 1,960. I'm not going to bother putting that up on my calculator because it's just the square root of 1,960. And that's 44.3 meters per second. There it is. We have a velocity. If you're going, what speed is that in like miles per hour if you're over here in the United States? Okay, so in miles per hour in feet, this would be just over 300 feet. A meter is just a little bit more than a yard. And so it's coming from 300 feet. That's a tall coaster. It's a really high one, but there's some out there that are that high. So this is possible. What kind of speed is this going to be? If we multiply 3,600 seconds as in 1 hour and 1,609 meters is in a kilometer, that'll give us kilometers per hour. If we take that number, multiply it by 3,600 and divide it by 1,609 meters per kilometer, sorry, meters per mile, that's a kilometer. And that is a whopping 99 miles per hour. Now you probably have not seen a 99 mile per hour roller coaster, but you have seen a 300-foot tall roller coaster. So there's one little takeaway in this, is that a roller coaster coming from about 100 meters is only going to go about 77 to 80 miles per hour, not 99. So what is the difference there? What are we missing if this isn't the exact value that we're going to get? Well, have you ever listened to a roller coaster? There's a lot of rumbling going on as it goes down. There's a fast-moving object. So don't forget your forces unit. As it's moving down, it's experiencing some drag backwards. And also, since it's rumbling, it's transferring energy to the track and the environment around it in the form of vibrations and sound. And also, there's going to be some heat. So there's going to be some friction and drag that are going to do some negative work to the system to keep it from going this fast. But oftentimes, if you just got a slower moving object, and if it's not sliding a whole lot, if you can reduce friction a bit, which is possible, then you can estimate your velocities in this way using energy. So with that in mind, just keep in mind there is some, well, in chemistry they use Q, so I was about to use Q. There's some heat energy that's also produced here, and that's going to take away from this velocity a little bit. In this class, we're going to say friction and air resistance are negligible, so we're just going for that value there. Okay. There's one more thing. I mentioned that one last thing here. One type of energy, I should say. I mentioned that gravitational potential energy is MGH. You might run into springs. So what if we put a spring on the end here? Spring is also has an elastic force. There's an elastic force that is also a conservative force, just like gravity. When you push in a spring, does it just stop like friction would do? No, it pushes back out. So there's also a potential energy from a spring. Sometimes it's an E for elastic. I'm just going to put an S for spring. And if you learn about a spring constant or how a spring is displaced from Hooke's law, spring force equals negative kx, then the potential energy from the spring is 1/2 times the spring constant times x squared. If you're not working with that in this class, just be aware that springs also have potential energy, and all you would really need to do is plug that in for any potential energy of the spring. So that's just a little bonus there. 2 types of potential energy and 1 type of kinetic energy. Okay. Now I'm going to just expand as one last example here. What happens if we have a coaster that has an initial velocity, and what if it's not going down to the bottom of the track? Say it goes down to the bottom, but what if there's a loop next? I'm going to start this out the same way. We're going to have an initial height of 100 meters for a roller coaster. But when it's on this loop, it's upside down here. Let's say it goes back up to about, what's that look like? 60, 70? I'm going to call 0.1 over here. Actually, let's call that 0.2 and just 0.1. We're not going to solve 0.1 again, okay? Because we just solved this. It's going at about 44 meters per second down here. It's 44.3. Okay, but what about if it goes back up to a height of, it's about half, height of 60 meters? Okay, so height at 0.2. That's just kind of sloppy there. So I'm gonna write it on drawn on this side. .60 meters height. All right. Also, I'm going to give this a little nudge. What if it has an initial velocity of 5 meters per second? Usually coasters are rolling a bit before they start taking their big plunge. If this has a 5 meters per second start, how fast is it going to be moving in the loop? Okay, let's check that out. Where do we start? Energy at one point equals energy at another. Whoa, what did I just do? I didn't go from 1 to 2. Nope, you don't have to. Law of conservation of energy says the total energy here will be equal to the total energy at any other port in the track. Next, let's figure out what kinds of energy are at point 0. Up here, we've got a height. I'll redraw that. Let's get our toolbox here. Gravitational potential energy is mgh. Kinetic energy is half mv squared. That's our start. Okay. So what kind of energy does it have? Well, does it have height? Yeah. So up here at the top, it's got some potential energy from height. Does it have velocity? If it has velocity, it has kinetic energy. Well, it does have velocity. That means the total energy isn't just from potential, it's from gravitational potential and kinetic energy. So you have potential and kinetic up there at the top. All right. What about right here? Does it have height? Yeah, 60 meters. That means there's potential energy in the coaster at this point. Is it moving? Well, it's lower than the top, so it should still be moving. If we had a coaster that went from 100 meters back up to 100 meters, in reality it wouldn't make it because of friction and drag. But it would start here. As long as it started with an initial velocity of 0, it would go back up to the same height over here, then go back and forth infinitely, forever. All right, but what about any point lower than the top? It's moving there. And that's really what we're looking at here. This object, this roller coaster is going to be moving here, not with as much velocity as at the bottom, but with more velocity than at the top. So there is going to be some kinetic energy here also. That's gravitational potential energy. All right. So let's move over to here now. At point 0, there is gravitational potential energy at point 0 and kinetic energy at point 0 equals the potential energy at point 2 plus the kinetic energy at point 2. Okay, there's potential and kinetic at point 2 also. Right there too. If I didn't put the 0 and the 2 on, these would look exactly the same on both sides. It might look kind of confusing, like what am I supposed to do here? There's no differences. But now we're going to see. All right, this expression is going to expand out a little bit before it comes back together when we plug in our numbers. Whenever you see PE, you're going to substitute in mgh. mgh. And this is in the beginning, so we're going to put a height of 0 in the beginning. And we got a kinetic energy, 1/2 mv squared. And again, this is at the beginning, so we'll put a 0 there. We got potential energy at point 2. mg height at position 2. And the kinetic energy, 1/2 mv squared, and the v is at position 2. Remember, this is a subscript over here, and that's a square value. This is a mathematical operation, and this is just a label for the velocity. Not good. Just don't get those confused. Okay, now Let's see what we've got. Well, we don't know the M. Don't let that bother you, remember. Might cancel out here, should. Height at position 0 is 100 meters. Next we got a 1/2 m. The initial velocity is 5 squared. Now we're looking at point 2. Plug in a 9.8 for the G. A height of 60 this time. And Shelley often runs out of space here. Plus a 1/2 m v2 squared. And that's our unknown. That's the one we're looking for. That's our target variable. All right. We've got an m times 980. That looks the same as before, but now there's a 5 squared. That's a 25, right? So 5 squared is 25. I'm going to go ahead and plug in a 25 there. Equals 9.8 times 60 is 500 something. Let's get that. $588. So we got an m times 588 plus 1/2 m v2 squared. Now, it might be a little easier to see that these m's will cancel out. If I divide out m from every single term, so I have a little error here. There should be a plus sign, not an equal. Okay, so, yep, potential plus kinetic there. Divide out m on all these terms, and they cancel out. Don't be too quick to do that. Sometimes they don't all cancel, so you might need a mass at some time. Now we've got a 980, and we're just going to simplify from here. Half of 25 is 12.5. See, there's not a whole lot of kinetic energy to start with. A lot of potential, but not much kinetic. 588 plus half v2 squared. All right, this turns out to be a 992.5. And subtract 588 on both sides. 404.5. Thought I was a little off on that one. Okay. 404.5. And we're going to multiply both sides by 2. Pretty sure I can get that one. So that 1/2 and the 2 cancel there. This is like 808, but plus a half is 809. Equals v2 squared. And we'll take the square root. So we get our velocity at point 2. Should be considerably less than at the bottom. It's the square root of 809. It's 28.4. We're still moving pretty fast there. Good speed. All right, that's how you do it. Just recap. Look at the energy. Energy at one point equals energy at the other. Figure out what forms of energy there are. Once you figure out the forms, plug them in for the initial and the final, and then substitute their expression for potential energy, expression for kinetic energy. Plug in your known values, see if anything cancels, work through the algebraic equation, and that's it. And that's the end of this episode.